students. In this lecture, we are going to see the discovery of electron and the nucleus, and we will also see that how the electron and the proton, they are present in the atom to make a stable structure. So first is the learning outcome of today's course. In this lecture, you will be able to understand the experiments that led to the discovery of electron and nucleus, and how classical mechanics cannot explain the structure of atom. So let's first have the recap of the previous lecture. In the previous lecture, we discussed the observations of scientists that led to the initial but wrong belief that atoms are the smallest particle that constitute matter. Now we know that existence of atoms is correct, but they are not the smallest particle of matter. Dalton, an English school teacher, he put together all the observations of Boyle's, Lavoisier, and J.L. Proust to formulate Dalton atomic theory. According to Dalton atomic theory, the atoms are the smallest particles and they constitute the matter. They can combine to form compounds, and the atoms of one element are identical with each other. And we also discussed the scanning tunneling microscope, what is the working principle of STM, through which we can photograph the atoms. Now today we are going to see that atom is split up. It can be split up into at least an electron and a proton. The experiment that led to the discovery of electron is called as the J.J. Thomson experiment. J.J. Thomson was actually interested in understanding the deep discharges in the gas discharge tube, and he was studying those discharges, the nature of the discharge that is created in the glass tube. So he used a glass tube which was evacuated, and this glass tube has a negatively charged cathode in it and a positively charged anode in it. And after evacuation of this tube, he filled this gas tube with hydrogen gas. There was nothing else in the gas tube. There was only hydrogen gas in the gas tube. Now what he did, he increased the potential difference at the cathode and at the anode, and he increased the potential difference until the gas inside this tube, it started to glow and the discharge is created. A discharge is ignited, and this discharge, you can see it in the form of the bright light which is created from the cathode to the anode in the gas tube. So this discharge is actually a kind of plasma, and he wanted to understand the nature of this plasma. He wanted to understand that what constitutes this plasma, what is present in this plasma. So in order to understand this, he did some modification in the experiment, and what he did, he put a small hole inside this anode, the positively charged electrode, and he lets this plasma out, and this plasma can move out of the gas tube and it can strike with this surface which is called as the phosphor screen. And what happens that when this plasma, it goes straight and it strikes to this surface, it creates a glow at this position where it strikes into the phosphor screen. So this was the indication that this was moving through this place and it is striking on this point, and it also displayed the path of this plasma or discharge which was created in the gas tube. So this was a simple experiment. He further wanted to understand the nature of the plasma, whether they are positively charged or negatively charged. So he also did further modification in this experimental setup. He put two plates above and below this discharge tube. One of the plate is called as a positive plate and the other is the negative plate, and they are deflection plates because we will see further that they caused the deflection of the beam or the plasma. So when he applied the positive potential on this deflection plate and negative potential on this deflection plate, he saw that some of this discharge that was moving straight earlier, it was deflected towards this positively charged plate and it now strikes at this position on the phosphor screen. So there was a difference between these 2 points. Then he measured that difference, and this is called as delta X. and he named that delta x as delta x negative because these particles were deflecting towards the positively charged plate and therefore they must be negative. So he called that this is the deflection and he called it as a delta x. So one point was obvious from this experiment that there are some negative particles in this beam that are getting deflected towards the positively charged plate. Now he did some further experiment. He increased the voltage on the deflection plates and he realized that there are actually some other particles that are deflected towards the negatively charged plate. Again, let's see this experimental setup. He then increased this potential difference between the positive plate and negative plate. When he increased it, he found that some of the particles were also deflecting towards this side, but they were very small and the deflection was lesser. But there were particles who were deflecting towards the negative plates. So he also measured that deflection. He called it as delta x plus because they were deflecting towards the other plate, towards the negative plate. So he said that they must be positively charged. So their delta x is proportional to the charge in the positive plates, so positive particles. So he also said that if the particle is of higher charge, then that deflection will be high. If the particle charge is less, then the deflection is less. So he said that this deflection is actually directly proportional to the charge on the particle and it is inversely proportional to the mass of the particle. Similarly, for the negative particles, the deflection is directly proportional to the charge on that particle and it should be inversely proportional to the mass of the particles, because if the particles are heavy, they will be deflected less. So what did he interpret from these experiments? There were the few interpretations that were made from this experiment. He said that luminous beam, that is the discharge, is deflected to the positive plate. It must be negatively charged particle. And later on, these particles were called as the electrons. Now he guessed that the positive particles which are getting deflected towards the negative plate, they must be hydrogen ions H+. Why he called this? Because he knew that in the discharge tube there are only hydrogen atoms, and if you remove some negative particle, let's suppose this is the hydrogen atoms which are present in the gas tube and there is nothing else in the gas tube, and if we remove these negative particles from the neutral hydrogen atom, then we are left with some positive hydrogen ions. So he said that the positive particles that are getting deflected towards the negative plate, they must be the hydrogen ions. Then further he interpreted that magnitude of the charge on the negatively charged particle is equal to the magnitude of charge on the positively charged particle. That is, the magnitude of the two charges is equal. And that is also obvious from this figure. If you have a neutral hydrogen atom and if you remove some negative component from here, then the positive charge which is introduced into the system will be equal to the negative charge which is removed from the system. So the deflection for the negatively charged particle was much larger. He said that the negatively particles that were electrons, they were lighter, and he observed in the experiment that the deflection of the negative particle was much higher and the deflection of the positive particle was much lower. So this was the interpretation that delta x negative was much higher than delta x positive, which implied that mass of the positively charged particle, here I am representing E plus, the protons are represented by E plus, then the mass of the positively charged particle is much higher than the mass of the negatively charged particles. So these were the few interpretations that he did from the experimental setup. So based on this experiment, he proposed the structure of atom. Structure of atom because there were only hydrogen atoms in the gas tube. So based on the interpretation, he proposed that what could be the structure of hydrogen atoms. And he suggested that hydrogen atom consisted of a positively charged pudding or space inside the atom, and which is surrounded by the negatively charged electrons, and it's like plum pudding model because we have electrons like a plum in the pudding which is positively charged. So he proposed this plum pudding model based on the experiment that he did to study the discharges. So through this experiment, the electrons were discovered, and it was discovered that this might be the structure of the atom, and it was also discovered that the atom is not the smallest particle. We have even smaller particles which are present inside the atom. Then the second particle which was discovered in the atom is the nucleus, discovery of nucleus, where Ernest Rutherford, and he did some experiment with the alpha particles. He had a sample of radium bromide from his friend, and because radium bromide is radioactive, so it was emitting some alpha particles. So he was doing an experiment to understand the nature of these alpha particles. What are these alpha particles, and what are they made up of? So at that time it was not known that what are the alpha particles. The only thing that was known was that they were charged particles and they are energetic particles. So this is basically the reaction that happens when the radium is converted into radon. This radium is radioactive, and by emitting these alpha particles having the mass of 4 and the atomic number 2, it is converted into this radon. So these alpha particles, he wanted to understand the nature of these alpha particles. Now we know that this alpha particle are actually the helium plus 2 ions, but at that time it was not known. So he was studying these alpha particles using an experimental setup. So basically this reaction, it releases an energy of 4.6 mega electron volt. It's not a chemical reaction, it's a nuclear reaction, and it produces a noble gas radon. And half-life is an important term in the radioactive reactions. It is actually the time required for the quantity of this radioactive compound to reduce to half of its initial value. So the half-life of these alpha particle disintegrations is very long, and usually these kind of materials they take billions of years to completely decay. For example, in this case, radium-226, the half-life is 1600 years. So what was the experimental setup? He had some radium bromide and alpha particles were emitted. He put a detector in front of it and he counted the number of alpha particles per unit time per minute. So he counted that there were about 132,000 alpha particles per minute approximately. So in order to understand the nature of alpha particle, he just put a gold foil which has a very small thickness, 10⁻⁹ meter. He put that alpha gold foil in between this detector and the radium bromide to see what happens, whether they are stopped or not, and what happens to the alpha particles. So actually nothing happened to the alpha particle, and they just pass through it and reaches to the detector, and when he counted the alpha particles, they were almost the same, 132,000 alpha particles per minute. So this was not an interesting experiment for him because there was nothing he could deduce from this experiment. So he asked one of his students to create a detector which can be moved from one place to another. So he prepared a detector which can be moved at this place, and when he placed the detector at this place, then surprisingly he saw that some of the particles, they were getting detected on this site, and he noted tick tick ticking on this detector indicating the striking of the alpha particles. So when he measured the rate of the alpha particles, they were very less as compared to the alpha particles that were going through the foil, but there are some alpha particles that are backscattering from this foil. So this was something interesting. He wanted to understand the alpha particles and the nature of alpha particles. So he calculated the probability of these backscattered alpha particles. And for calculating the probability, what he did, he counted the number of particles that are being emitted, and the total particles were 132,000. So what he did, he divided the count rate of the backscattered particles by the particles that were passing, 132,000, and he get the probability 2 into 10⁻⁴. So this is a very less probability of the backscattered particles, but it is some number. So it means there are some particles which are backscattered for some reason to this detector. So he made some conclusion from these experiments. He said that most of the alpha particles, they pass through the foil. It means the gold atoms which are making the gold foil, they must be mostly empty. However, occasionally, once in a while, not very often, but occasionally, some of the helium ions or the alpha particles, they hit something massive, and which causes them to backscatter and move back towards the detector. So now, from knowing these scattering probabilities, backscattering probabilities, and from knowing the size of the atom and the thickness of the gold foil, he could calculate the diameter of the nucleus. So he called that something which is present in the atoms of the gold, which are backscattering the alpha particles. He named them as a nucleus, which is present in the atoms of the gold, and he calculated the size of that nucleus from the knowledge of the scattering probabilities and the size of the gold atoms and the thickness of the gold foil. He calculated the diameter of the nucleus, which was found to be 10 to the minus 14 meters. So he named this thing the central massive thing, which was backscattering the alpha particle, as a nucleus, in analogy to the massive center of a living cell. Now he also knew that nucleus had to be positively charged. Why it has to be positively charged? Because he knew that the atoms, the gold atoms, they are neutral, and we already knew that electrons are part of the atom. Electrons are present in the atom, as we know from the J.J. Thomson experiment. So he was sure that this other particle which is present in the atom, it must be positively charged because the atom is on the whole neutral. So his model of atom is that there are Z number of electrons that are present in the atom with the central positively charged thing in the center that has a diameter of 10 to the power minus 14 meters. So it is important that this kind of Rutherford backscattering experiment is also the basis of experiment that was done to discover the quarks that made up the proton and the neutrons. So these quarks were determined by the same kind of Rutherford backscattering experiment. So here is a pictorial interpretation of the two kinds of model. After the discovery of electron by J.J. Thomson, we had this kind of plum pudding model where the positively charged pudding and the electrons are present inside it. But after the Rutherford experiment, the presence of nucleus in the center, which is positively charged, is determined. And he said the electrons are surrounding this positively charged, and if the alpha particles are passing through the atom, some of them can be backscattered through this positively charged nucleus. So now the structure of atom was transformed from the plum pudding model to the new atomic model. Now the question is that we have positively charged nucleus and negatively charged electron in the atom. So there are two oppositely charged things, how they are held together in an atom and how they are making it stable. Because if they combine together, they will neutralize each other and they will not exist separately, and the structure of atom will be destroyed. So we want to know that what kind of the force is holding them inside the atom so that they are also stable. So generally we have four kinds of forces. The gravity is the gravitational force between any two massive objects. So it cannot be a gravitational force. Electromagnetic force is the interaction of particles with electrical charges. So it can be electromagnetic because we are dealing with the positive nucleus and the negative electron. Strong force is a kind of force which keeps the nucleons together, that is protons and neutrons together. And there is a weak force, which is also a very powerful force, and it causes a phenomena such as beta decay. It governs the decay of unstable subatomic particles such as mesons and initiates the nuclear fusion reactions that fuels the sun. So these strong forces and weak forces are the intranuclear forces which are present inside the nucleus, and that what keeps the protons and neutrons and the quarks together. So here we understand that we might be dealing with the electromagnetic interaction because we are dealing with the positive and the negatively charged particles. Now the electromagnetic interaction is explained by the classical law, which is called as the Coulomb's law. So let's see that whether the Coulomb's law can explain the stability of an atom or not. So if we have a positively charged nucleus and a negatively charged electron at some distance r. Then we have the Coulomb's force, which is given as F is equal to the positively charged magnitude of the positive particle, magnitude of the negative particle divided by 4 pi epsilon naught into r square. So it's an attractive force, and epsilon naught is actually the permittivity of the vacuum. And now from this formula we also see if r is equal to infinity, then the force will become 0. And if it's r is equal to 0, then this force will become very large. So if we have two particles and we let the two particles go, if we leave them, they will be attracted toward each other because they are oppositely charged, and they will move towards each other. So now we know that if r is equal to 0, then the force will be maximum, and if r is equal to infinity, the force will be minimum. But we don't know that what happens if we leave the two particles and they move toward each other, with which time they will move toward each other, and how they will cover the distance. So we don't know the movement of the particles as a function of the time. So the problem is that above equation does not tell us how r changes with time, in how much time these two particles will collide with each other. R as a function of time is not known, and in how much time electron will combine with the proton, and what is the stability of atom. So we are not able to predict the stability of atom. So now we want to understand that how the R will change with the time. This can be done by using the Newton's law, which is also another classical equation, which is F is equal to ma. Here you see that acceleration can be written as the change of velocity by unit change in time, and again the velocity is a change in the distance per unit time. So we can get this equation mdr square divided by dt square. So if we put the value of the Coulomb's force into the Newton's law, there is a way that we solve this equation. So if we put the value of the Coulomb force here, and this force is equal to this one, and we solve this equation, then we can get the r as a function of time. So we will be able to see that what happens if the two charges are attracted towards each other. So if we solve this question, we will see that in just 10 to the power minus 10 seconds, the electron will neutralize the proton, or in other words, the atom will be destroyed, which is contrary to the reality because the atoms are very stable, and if they do not decay, and they do not electrons and protons, they do not combine to neutralize each other. So this is contrary to our observation. So these two classical laws, that is the Coulomb law and the Newton's law, this is predicting something which is not happening actually. So this shows that either the Coulomb's law is wrong, or F is equal to ma, that is Newton's law, is wrong, or maybe that the two laws, which are the classical laws, they cannot explain the electron and the proton interaction. So it means this leads to the conclusion that the classical mechanics cannot explain the presence of electron and proton inside atom, and it cannot explain the stability of atom. And we now know that a new kind of mechanics, that is quantum mechanics, is required to explain the structure of atom. That we will be discussing in the next lecture. Thank you.